All right, we have talked about a little bit about these constant acceleration kinematics equations, which are, again, it's important to remember, they're only true if ax is constant. That means you need to know what x means. You have to have defined your axes. In between two times, then these say if you know what x is at the initial time and what Vx is at the initial time, you can figure out what x is at a later time, or Vx is at a later time. And we're going to now specialize to one particular very important case, which is called free fall of an object near Earth's surface. So the idea with free fall is if you're near Earth's surface, in other words, anywhere on the surface of Earth, every object in free fall is going to fall the same way. Free fall means gravity is the only non-negligible force on it. And I know we haven't talked about forces yet, but we will shortly in chapter 4. And for right now, you're just going to use your intuitive notion of force. So gravity is the only important pull on this object while it's in flight. So it's not going to apply if I'm holding it with my hand, because then my hand would be exerting a force on it, right? Or when it hits the ground, it's not going to apply. But if it's just dropped and it's in mid-flight, if an object is in free fall, it's going to accelerate toward Earth with the same magnitude of acceleration, and that acceleration towards, in the direction straight down towards the center of the Earth is 9.8 meters per second squared, and we denote that by a lowercase or little g. So little g is 9.8 meters per second squared. That means that it doesn't matter what the mass of anything is. And by the way, this little g is called the free fall acceleration magnitude. It's how fast things will fall if you drop them or even throw them up. We'll give examples of that shortly near the surface of the Earth. The acceleration is the same regardless of an object's mass. So you can take, in fact, I would have done this if I were doing this in front of you in class, a light ball, maybe a ball made of rubber and another one made of metal, so it's really heavy, and I can drop them, and we would find that they hit the floor at the same time. They have the same height at all times, so their acceleration is the same. If their velocity is the same at all times, their acceleration would be the same. And if you do experiments, you can show that the rate at which they're accelerating is 9.8 meters per second squared. Doesn't matter what the object's mass is, but air resistance has to be a negligible force. Air resistance is the force, how much pushing the air is doing on the object. So if I'm dropping a ball, normally if it's falling from a few feet above the floor to the floor, in that range, gravity's pulling on it with a substantial force, and the air is hardly pushing back at all. But it can be true that if I drop something from the top of a building, it might go so fast that even though gravity's pulling on it with a substantial force, when it starts going fast down, the air resistance can be pushing up on it. There's a lot of air force. The faster it goes, the bigger the air force. So air resistance has to be negligible. And another way of saying that is the object's speed through the air can't be close to its terminal speed. Its terminal speed is, if I drop an object from a skyscraper, it probably, after accelerating for a while, will start to get closer and closer to having a constant speed downward through the air. So it can't be close to that. Usually we're talking about things that are thrown up or dropped near the surface of the Earth. Certainly for most kinds of balls, we would expect them to behave that way, or rocks or things like that. If I drop a plastic bag or something like that, it's certainly not going to fall at the same rate as a ball. So in there, air resistance would be an important force for that plastic bag. But usually it'll be pretty clear from the context whether we're talking about things where air resistance is negligible. So here's an example, or just a cartoon of someone dropping a ball off a cliff, and we could say as long as air resistance is negligible for this ball, it's a fairly dense ball, the acceleration of this ball would be downward towards the Earth with a magnitude of 9.8 meters per second squared. After it's fallen a little bit, and it's going a little bit faster down here, right? It's picked up some speed, its acceleration is still 9.8 meters per second squared in the direction downward as it's falling. That's not only true for things that are just falling. Free fall includes things that are going up. It sounds like they're only going down, but free fall can include things that go up and then come down. So in this case, we would say after this person has released the ball from their hand, the acceleration is constant all the way up and all the way down. So in other words, after being released from the hand, the acceleration is downward with a magnitude of 9.8 meters per second squared. At the very highest point where it momentarily comes to rest, its acceleration again is 9.8 meters per second squared in the direction downward, and its acceleration after it's fallen and is passing the point where it was released is still 9.8 meters per second squared in the direction down, assuming air resistance is negligible. So we would call this whole process a free fall. That ball is in free fall on the way up and on the way down, strangely enough. Now, in order to know what AX or AY is, we need to set up some axes. So, for example, if I choose plus X to be upward, I know that the acceleration is always in the direction downward. So if my acceleration vector points downward, that means to go from the tail, well, I guess I should say that I've forgotten we haven't talked about vectors, but in any case, the acceleration is in the direction downward. If I were accelerating upward, that would correspond to a positive AX. So if it's accelerating downward, it is a negative AX value. So if I choose plus X up, AX is constant at minus 9.8 in SI units, minus 9.8, minus 9.8 as it goes down. I'm perfectly welcome to choose, well, I'm sorry, in this case, if I choose plus X is up, when we're using those constant AX kinematics equations, we're going to plug that constant AX into the kinematics equation. So everywhere I see an AX, I would use minus 9.8 in SI units in that particular case. Now I'm perfectly welcome to choose the opposite convention, that plus X is downward. If I choose plus X is downward, then it's accelerating in the direction downward. That's a positive acceleration, and so my AX would be plus 9.8 in this coordinate system that I chose. So plus 9.8, plus 9.8, plus 9.8, all the way up and all the way down. And when I plug into those kinematics equations, I have to use a plus sign and not a minus sign for AX. It's my choice, and it doesn't matter really which choice you make, but you do have to make a definite choice and pay attention to those plus or minus signs when you're plugging in to the kinematics equations. Let's start with a simpler example here, solving a problem using the kinematics equation. So this is a case where if something's in free fall, then the acceleration is constant. And if the acceleration is constant, I can use those kinematics equations. So here, a stone is launched via a slingshot straight upward at 12.6 meters per second. If we ignore air resistance, or if it's negligible, what maximum height above the launch point does it reach? In other words, it's launched upward. How high does it go above the launch point before it comes momentarily to rest and then starts coming down? What is that distance that it goes? So I need to be very clear about which direction plus X or plus Y, it doesn't matter whether we call it X or Y, but for some reason people like to choose Y when we're talking about vertical motion. So here we'll define a Y-axis for a one-dimensional motion. Let's decide to choose plus Y is upward, and we'll take, just for simplicity, Y equals 0 to be by definition where it's launched from. I don't have to choose that, but it seems reasonable and simple. And also for simplicity, let's say the time when it is launched from, it's just released from the slingshot, we'll call that by definition t equals 0. And the final time, that is going to be defined by when it reaches the highest point. So t equals 0 is right when it's released from the slingshot. T final, which we'll just call t, is the highest, is when it reaches the time after that, when it reaches the highest point. Okay? And what do we want to find here? Well, I guess I have it phrased here in terms of, this is the difficulty with not writing on the board, is I, sometimes I'm surprised by the order I do things. But here, we're defining first what we know. So I know in this case, if I've chosen plus y to be up, the initial y velocity is 12.6 in SI units. And notice I'm being kind of lazy. I didn't put the SI unit of meter per second there because, gosh, it's going to be so annoying to always have to write those units down. And we can be a little bit lazy about it because we know that when we look at these equations, they're dimensionally balanced equations. And as long as if I'm solving for some variable in one of these equations and I put all SI units in for everything else, then I know I'm going to get SI units out. So as long as I'm using all SI units, I'm just going to suppress the units and be a little bit lazy. And then at the end of the calculation, I'll say, oh, I'm talking about a velocity, it's in meters per second. Or I'm talking about a position, it's in meters. Because I put all SI units in, and I'm getting X, the units for X must be meters. Okay, so suppressing the units, Vy initial is equal to 12.6. It's positive because it was going upward and plus Y is upward. Ay is minus 9.8. It's accelerating downward, but plus Y is upward. So that would have units of meters per second squared. And by definition, we said the final time is when it reaches the highest point. And so Vy, which represents the final Y velocity, is 0 because it momentarily comes to rest at that highest point, and that's what we're calling final here. Okay, that's what we know, and what we want to know is, oh gosh, I see a typo here. This should say we want to know y or delta y, right? We want to know if it starts out at y equals 0, we want to know y final, because then y final would represent how far it's gone up. Or we want to know delta y, which is y final minus y initial. So this should actually say y right over here. Okay, so given what we want to know and what we know, again, I know this is a little bit similar to the previous problem, but we aren't asked anything about time, and we don't know anything about the time it takes to go from that at launch point to the highest point. So we don't know anything about time. We don't want to know anything about time. It seems like we probably, at least as a first guess, would like to try using the equation that doesn't involve a t in it, because it's not going to help us at all. So let's try substituting into that equation. Just rewriting it down here and plugging things in. Vy final, we said, is 0. Okay, that defines final. It's whatever the time is when the velocity momentarily comes to 0 at the highest point. Vy initial is 12.6. That's positive with our axis convention, and ay is minus 9.8. So important that you get those minus signs correct in here. And the thing we want to solve for is delta y, and all I can do is plug those in, bring this one over to the other side with a minus sign, and then divide by this negative number that's multiplying there, and we get delta y as 8.1 meters. So after release, it goes up 8.1 meters before momentarily coming to rest and then starting to fall down. That's kind of an interesting piece of information that it wasn't obvious that we would be able to calculate that, but it's pretty easy with the kinematics equations. All right, why don't you try to do a kinematics problem using the idea of free fall. So again, here's something that's going to involve at least part of this problem is free fall. Now it's a little bit more complicated than the ones we've been doing, so try your best at it. It involves a helicopter, and there's really two parts to the flight of this helicopter. Initially, the helicopter rises vertically at a steady speed. Okay, notice that is constant acceleration motion, but the acceleration happens to be 0 in this case. If something's going at constant speed upward, its acceleration is 0, but that's constant acceleration motion. And then, when it reaches a height of 115 meters, the engine suddenly stops. And after the engine stops, we're going to ignore air resistance on the helicopter. So that means after the engine stops, it's in free fall. And we're asked a couple of questions about this. How long does it take the helicopter to reach a height of 115 meters? How long after the engine cuts out does it take for the helicopter to crash on the ground? And there's a third part to this problem too, which I didn't have room to put on this slide, and I'm forgetting what it is now, but something related to it crashing on the ground. Sorry for the morbid problem there. In this case, you have to be careful. There are two different time periods for the problem. One is when it's rising steadily at 7.2 meters per second, the acceleration is constant at 0. When the engine suddenly stops, then it's in free fall and the acceleration is non-zero. It starts accelerating downward. So I can't for example, I'll use the kinematics equations where I take t equals 0 to be when it begins rising and t final to be when it reaches its highest point, because some point before it reaches its highest point, it starts becoming in free fall. In other words, it's rising at 7.2 meters per second. When the engine cuts out, it doesn't suddenly start falling. It rises just a little bit more before it starts falling down. And so you have to be careful that you only use the kinematics equations when during a time period where the acceleration is constant. It's constant at 0 during that initial time period. Then after that 115 meter height is reached, it's constant at 9.8 in the direction downward for the rest until it crashes on the ground. All right, so try your best at doing those. This is kind of a difficult problem, so try your best and come back and we'll do the solution in the next video.